Hey everyone, let's discuss BCNF. I already discussed 1NF, 2NF and 3NF. In 1NF, every attribute value should be atomic. In 2NF, there should not be any partial dependency. In 3NF, there should not be any transitive dependency. 3NF is good for primary key, but when it comes to candidate key, 3NF cannot handle multiple candidate key. That's why we move to BCNF. The following two cases cannot be handled properly by 3NF. That's why we use the BCNF. One, if the relation consists multiple composite candidate key and if there are overlapping attribute in the candidate key. In that case, 3NF cannot handle it properly. That's why we use BCNF. 3NF mainly focus on primary key. That's why it's good with respect to primary key but not good with respect to candidate key. A relation schema is said to be in BCNF if it is already in 3NF and all determinants are key. Determinant means the left side. Right side are dependent, left side attributes are determinant. So all left side attributes are key. A relation schema R is in BCNF with respect to F of functional dependency if for all functional dependency in F plus of the form A implies B, where A is subset of R, B is subset of R, means A and B both belongs to R, at least one of the following condition hold. First, A implies B is a trivial functional dependency. Trivial means B is subset of A. Second, A is a super key for schema R. If B is a subset of A or A is a super key, then we can say it is a BCNF. Let's see one example. ID implies name, department name, salary. Here ID is a key in the instruction relation. So that's why it is in BCNF. Let's say another example. Department name implies building, budget. Here building and budget both dependent on department name. Department name is the super key. That's why this is also in BCNF. So every determinant should be key. If every determinant are key, then that is in BCNF. We have the same definition for 3NF. BCNF and 3NF definitions are almost same, just little bit difference. Now see 3NF definition. I already discussed 3NF with respect to transitive dependency. Now see another definition of 3NF. A relation schema R is in 3NF with respect to set F of functional dependency if for all functional dependency in F plus F positive closure of the form A implies B, where A is subset of R, B is subset of R and at least one of the following hold. First, A implies B is a trivial functional dependency. That means B is a subset of A. Second, A is a super key for R. Third, each attribute in B minus A is contained in a candidate key for R. That means any attribute rather than A should be part of the candidate key. So B minus A should be part of the candidate key. Up to this is the BCNF definition. Including the third one, it is 3NF. So you can say BCNF and 3NF both are almost same. BCNF is the more restricted version of 3NF. Let's see some example of BCNF. Example 1. R equals to A, B, C, D, E, F, G, H and some functional dependencies given. First we need to find key. Here key will be AB as AB positive closure equals to A, B, C, D, E, F, G, H. It contains all the attribute. Then key can be F, B, C. Now in 2NF there can be two relation. R1 that contain AD. In 2NF there should not be any partial dependency. R2 that contain rest all. A, B, C, E, F, G, H. Now in 3NF there should not be any transitive dependency. So we'll separate F and G. Now R1 will contain AD, R2 FG, R3 A, B, C, E, F, H. Now in BCNF we'll separate F, B, H. H is dependent on FB and every left side should be super key. Okay, so that's why R3 FBH, R4 ABCEF. Now in R1 here A is the key, R2 F is the key, R3 FB is the key, R4 AB is the key. So every table have key. Let's say another example, example 2, R equals to A, B, C, D, E, F, G, and there are some functional dependency here. Key equals to BC. BC positive closure contain all the attribute, that's why key is BC. Now in 2NF there should not be any partial dependency. So which is dependent only on B or only on C, that will separate. Here C implies D, that will separate in 2NF. In 2NF there will be two relation R1 CD, R2 A B C E F G. Now A implies F, A implies G, then F implies G. So all are transitive. A implies F, F implies G. A, F, G cannot be in one relation, right? So there are lots of transitive dependency. We need to separate that. R1 CD, R2 FG, R3 AF, R4 AG, R5 ABCE. And this is also BCNF when there is just one candidate key, 3NF equals to BCNF. And you just see in R1 C is the key, R2 F is the key, R3 A is the key, R4 A is the key, R5 A B are the key. So in every relation there are key, and every relation comes from the functional dependency where left side are the super key. Let's say another example, example 3, C implies D, C implies A, B implies C. Here key equals to B. B positive closure equals to B, C, A, D, all the attribute, that's why key equals to B. Now 2NF, there are no partial dependencies, so 2NF will contain A, B, C, D. Now in 3NF will separate C, A, C, D from BC. So there will be BC, CD, CA. 3 relation, and here 3NF equals to BCNF as there is just one key. And after split, maximum we can go 2 attribute. Here every relation contain 2 attribute, so we cannot separate anymore, we cannot decompose anymore. This is the last. Next example 4, B implies C, D implies A, here key equals to BD. There are partial dependency, A is dependent on D and C is dependent on B, where B, D both are key. That's why 2NF, 3NF and BCNF all will be same. It will be BC, DA and BD. There will be 3 relation. One relation for BC, another for DA, another for BD. In today's lecture I discussed BCNF. In BCNF every left side attribute should be super key. I already discussed 1NF, 2NF and 3NF. Just go through previous lecture, and if this lecture is helpful for you, please like, share and subscribe. Thank you. Bye bye.